everybody. Thank you very much for joining us here today. This is Paul Taubman with 9.Connects. You're in the right place if you are here for our webinar on practical aspects of signal integrity. This is part 3 of the series. Today is our presenter, Tom Cassidy. And I will note that prior to handing the comm to Tom, we will have some time for some questions. So do take a look at your panel there and make sure that you ask those questions. He'll definitely take a look at those at the end. Anything that we cannot answer, we'll certainly try to get back to thereafter. So enough of the housekeeping, let's get on with it. With that, Tom Cassidy.
Hello everyone, and thank you for joining me for part 3 of the 9.Connects webinar series on practical aspects of signal integrity. My name is Tom Cassidy, and I'm a senior engineer at 9.Connects. I've been working in and around the field of electrical engineering for over 35 years. I've also dabbled in other areas such as mechanical engineering, applications programming, FPGA design, and simulation of both mechanical and electrical systems, and of course the field of signal integrity, which is the topic of this webinar. My intent for this webinar series is not to teach signal integrity per se, but to present you with a series of PCB layout design cases and show how we can apply signal integrity analysis to our designs. We can then use this analysis to help find and fix any problems we might have before we commit to the time and expense of actually fabricating and debugging the circuit board. In parts 1 and 2 of this series, I've focused on the analysis of the signal integrity aspects of a single element associated with PCB routing, such as the trace size and length, the use of vias, how reference planes work, and so on. We were interested in seeing how the signal integrity of the physical aspects of these different PCB elements would affect the signals, causing effects such as signal degradation, ringing and overshoot, increased rise times, and so forth. Since I was looking at relatively small layout elements and was making relatively small changes to them, I generated simulation data in the frequency domain. Known as S parameters, these graphs provided an easy method of measuring and comparing how the different routing paradigms would affect the integrity of a signal. S parameters are essentially a graphical representation of how the interconnects affect the signal over a range of frequencies. As such, the S parameter graph provides a good way to see the signal integrity differences, both large and small. In part 3, I'll finally be getting around to presenting the DDR3 design that I've been wanting to do since the beginning. I'll talk more about the actual design in a minute, but first I'd like to discuss the change in my presentation methodology. Up until now, I've been looking at the signal integrity aspects of single elements of a PCB layout, but this process will no longer be sufficient when examining a full DDR3 design. Instead, I need to look at the timing relationships between different signals, and indeed even between and within different groups of signals. The reason for doing this is evident by reading through the datasheets and tech notes for DDR3 devices. Doing so reveals an almost mind-numbing number of rules and restrictions relating to the timing of various signal groups. When analyzing the operation of the entire DDR3 design, I will therefore move the focus out of the frequency domain for the most part and instead use time domain analysis as my means of comparing various test cases. However, when I start looking at individual elements within the DDR3 design, I may revert back to the frequency domain and present S parameter data as well. I'm also going to change up my presentation method a bit and this time start with the finished design instead of building up from simple layout cases as I did in the previous webinars. I'll also use an example layout in which I was easily able to follow all of the best practices suggested for DDR3, and thus is as close to an ideal layout as I could get. I'll then look at some of the design elements that are critical for DDR3 operation, such as the need for termination and length tuning. I'll also examine the issues surrounding the use of flyby versus T-branch routing. And in the course of these examples, I will also explore some of the real-world implications caused by common constraints and other issues that might force you to make trade-offs during your layout. I'll explore the signal integrity effects of these trade-offs and hopefully offer some guidance in your decision-making. So before I get started, here's a summary of what I'll be presenting today. First, I'll start off with a full DDR3 design and analysis. Then I'll move into looking at some of the elements within those designs, such as differential pairs, termination, flyby versus T-branch, and crosstalk. And as I said, I'll explore some of the ways the real world messes up our perfect designs and layouts, such as gaps in our paths, length tuning, and so forth. But first, let's take time out for a quick polling question. The polling question is, what is your DDR3 experience level? We want to know if you've done several designs already. Maybe you've tried them but couldn't get it to work. You haven't done one yet but are planning to, or you're just kind of interested in general. Okay, looks like we've got an interesting mix. Some fair amount have already done a design. A lot of people are just looking into it. Very interesting. Okay, well, let's go ahead and continue. Okay, let's get to the part you've all been waiting for, an actual DDR3 design analysis. Here is a block diagram of the designs I'll be using, which also coincidentally happens to be the project setup for the Cadence System SI simulation tool. I'll discuss the simulation in more detail later, but this gives you an idea of just how intuitive the simulation setup will be. For the memory controller, I will be using a Xilinx FPGA, one of the Zynq 7000 system-on-a-chip family of FPGAs. And for the memory devices, I have two Micron DDR3 DRAM chips, representing a typical 32-bit data bus running at 800 MHz. And in between them is the PCB itself. While not typically shown on a system block diagram, the traces and planes of the PCB play an important part when performing simulations and thus need to be represented. And this little block down here on its own is the VRM, or voltage regulator module. While also not typically included in a functional block diagram, the VRM needs to be present so that we can perform what is known as a power-aware simulation. By including the power subsystem in our calculations, we will be able to get even more realistic simulation results, which are often necessary to detect issues in high-speed designs. Now let's take a quick look at the schematic I used to generate the PCB. I won't go into much detail here since we'll discuss any specific items later as needed, but there are some aspects that will be informative right now. Here we see some of the same parts as on the block diagram: the Xilinx FPGA and the two DDR3 memory chips with their associated power and decoupling. We also have the termination resistors and power supply needed for the DDR3 address line termination. This wasn't shown in the block diagram since the simulator considers this as a part of the PCB itself. And here we see, at the schematic level, I'm representing the VRM as a simple 2-pin device that provides the 1.5 volt power needed for the DDR3 subsystem. Since we are really only interested in how the operation of the VRM supports our DDR3 design, and not really how it performs internally to itself, we do not need to go through the effort to simulate the entire switching power supply. It is sufficient to model the VRM operation at a high level, essentially as if it were an ideal power supply. This greatly simplifies the simulation calculations we are performing and does not really affect the accuracy of the final results very much. And now let's take a look at the actual layout. I'm going to use a design derived from a project I did a few years ago, early on in my DDR3 layout career. As such, it's not some of my best work, but it will serve as a good design case for this webinar. It also has the added bonus of actually having been built and tested. Here's a view of the top layer of the layout, with the traces shown in red and the yellow silkscreens indicating the placements of the parts. Here we have the FPGA as a 400-pin ball grid array on a 0.8 millimeter pitch, the two DDR3 memory chips, the termination resistors and power supply, and the connection points to our ideal VRM. And to give you an idea of the routing, I'll cycle through the top, the 4 inner routing layers, and finally, here is the bottom layer, which consists mostly of decoupling capacitors and some power and termination routing. Since I'm using impedance-controlled routing, I of course have sufficient reference planes in the stackup, and use the appropriate trace and space dimensions to give me the desired 40 ohm single and 80 ohm differential impedances typical of a DDR3 design. Okay, now that we have a full design, let's look into what it takes to actually do the simulation. As I mentioned earlier, we're now wanting to look at the higher level signal timings and interactions, and will therefore now use the Cadence System SI program. System SI, as the name suggests, is designed to perform the system level timing analysis we need in order to verify the operation of our design. Here is a view of System SI with our DDR3 design ready to go. As you see, it has the block diagram-like interface showing the major components of the design. We'll now take a closer look at each piece of this model. We'll start off by looking at the block in the middle of it all, representing the physical PCB itself. Since the PCB connects all of the other components together and carries the actual electrical signals, it obviously needs to model the actual copper traces and planes of the PCB in a way that lets us determine just how these electrical signals behave as we perform our high-level analysis. As you can probably guess, this means that we need to do a low-level frequency-based simulation that will derive a set of S parameters that we can plug into this model. System SI can then use these S parameters in conjunction with the pin models in the IBIS files to simulate the behavior of the actual signals. So for the PCB model, we need to go back to Power SI to do the frequency domain simulation. However, in the interest of time, I will not go through the actual details of this process. In reality, the process of setting up and generating the S parameters for the relatively large number of traces and discrete components used in this DDR3 design is a non-trivial exercise that takes a fair amount of time to get right. Once I had the board and the components set up, I was able to generate the behavioral data. Here is the resulting S parameter graph for this board. I am now able to go back to System SI and import this model file into the PCB module. We can now add in the models for the active components, which in this case are the controller and the two memory modules. At this level of simulation, the behavior of the controller is described by something called an IBIS model. IBIS, which stands for I/O Buffer Information Specification, is a means of allowing us to simulate the operation of the device right at its pins without needing to know any proprietary information about what goes on inside of the chip. IBIS essentially just describes the electrical operation of the pins themselves and leaves it up to the simulator to handle the wiggle the bits part, as it were. Okay, we now have all of the pieces in place in order to perform a simulation, the first of which will be for a data write operation. The results of this simulation will act as our baseline design case for future comparisons. Here is a quick overview that lists the parts of the design that we will simulate. And here are some of the simulation parameters we'll be using. We have a clock rate of 800 megahertz, which gives us a total data rate of 1.6 gigahertz. I'll be using a random data pattern with 16 writes per simulation. As I discussed, we have a real power model, and I'll be using 40 ohm on-die termination for the DDR chips. As a fun fact, it takes about 10 minutes to generate the PCB S parameters in Power SI, and another 10 to 15 minutes to run the DDR3 functional simulation in System SI. In order to do this, I'm using a fairly high-end system, and here are some of the specifications. Okay, with the simulation done, let's take a look at the results. This waveform is a straightforward time domain plot of the data bus signals as seen at the die pads of the DDR3 memory chip. It consists of an overlay of the lower 8 bits of the data bus. For clarity, I did not simulate the full 16-bit data path here. As you see, it looks pretty clean, which is what I expected since I already knew this board worked in the real world. Some of the things we want to look for are the upper and lower voltage levels, ringing and overshoot, and the transitions of the signal edges. Here is the same waveform, but with the positive data strobe signal included, shown in red. Since DDR stands for dual data rate, the data is being clocked on both the rising and falling edge of this signal. This is demonstrated here with some blue lines. Based on this waveform, it looks like things are okay, but it's a little difficult to make absolutely sure. So we can use a different kind of a waveform called an eye diagram to help us examine things in a different light. Eye diagrams are essentially a convenient means of examining the interrelated timing aspects of many signals at the same time. They are created by overlapping all of these signals of interest, triggered from a common clock edge. And as you see here, the end result is a diagram that has an opening in the middle, somewhat resembling the shape of an eye, hence the name eye diagram. I've now added in the data strobe signal, shown here in black. As I mentioned before, it is both the rising and falling edge of this signal that clocks data into the DDR device. As you see, the clock strobe transitions fall nicely within the middle of the eye opening, with lots of room on both sides and nice clean voltage levels on the top and bottom. In engineering terms, this is known as a good thing. Eye diagrams also let us measure a variety of parameters that tell us what is going on with the design. One such parameter is known as jitter. This is a measure of how far apart the transition edges of a signal are. In an ideal world, all signals would transition at the same time, but in reality, and even with the best layout possible, there will still be differences between trace delays. This shows up as jitter in the signal. Jitter is important because the worse it gets, the less width there is to the eye. This means we have less setup and hold time available for our signals, possibly violating the device specifications. Another thing that can affect the shape of the eye is the slope of the transitions themselves. As you see here, the transitions are pretty clean and relatively fast, as indicated by the slope of this line. Should the transition time of the signal get worse, for example by having too much parasitic capacitance, the slope would get worse and the eye would get smaller. The third main issue affecting the eye opening is that of overshoot and ringing. This affects the top and bottom of the eye. As it turns out, this is not much of an issue here since the layout was done correctly, but there is an easy way of changing this. I can simply change the on-die termination setting in the IBIS model for the DRAM, keeping everything else the same, and resimulate. Are you ready for this? Here is the eye diagram of the result. Remember, everything about this is the same except for the no on-die termination setting. Pretty dramatic difference, huh? As we see, there's a lot more ringing and overshoot, the transitions are noisier and the jitter is much worse, and as a result, the eye opening is almost non-existent. I'm pretty sure this would not work in the real world. While we're on the subject of changing simulation parameters to play what-if games, I'd like to tell you about a few other things that we can do to give us more information about the design. SystemSI gives us the option of connecting the PCB signals directly together instead of having physical traces. Known as auto short, this function essentially removes the signal integrity effects of the PCB from the equation and lets us focus on the active components themselves. Here is a slide with the eye diagrams from both simulation cases. As you can see, the auto short case is just as bad as before, if not even worse. This tells us that the problem is not with the PCB itself, but is being caused by the active devices, which makes sense since we deliberately turned off the on-die termination. There is also another useful tool known as pre-layout simulation. While it might not seem to make sense to simulate the design without even having the board layout done, it can actually provide extremely useful feedback about the design functionality early enough to fix any problems before spending time and money doing layout. You can then define the transmission line parameters any way you want, essentially emulating what you think the PCB will end up like before you do the actual layout. In the interest of time, I will not actually demonstrate this here, however. Okay, getting back to our regularly scheduled program, we've seen how we can simulate our design and generate some pretty waveforms and eye diagrams. But other than making some educated guesses, we still haven't provided a deterministic way of passing or failing the design. Fortunately, the electronics industry recognized this need and provides a set of standards and measurements that we can use to help us determine if the design will operate as expected. To help us with this problem, we turn to JEDEC, or the Joint Electron Device Engineering Council. Originally formed in 1944 to coordinate the naming conventions of vacuum tubes, JEDEC is an engineering trade organization that helps ensure interoperability amongst all products that conform to their standards. What this means to us is that if we simulate a design and the results meet or exceed JEDEC standards, we have a high level of confidence that the design will work in the real world. We are also fortunate that providers of simulation tools recognize the need to meet JEDEC standards, and have incorporated these standards into their simulation tools. So instead of having to manually interpret the waveforms and numbers generated by simulation, the tool generates a JEDEC compliance report for us instead. This extensive report is in the form of an HTML document and contains an exhaustive analysis of the design. Unfortunately, it is not in a format that lends itself well to my webinar display process, so I'm only showing a few sections of the report as examples. Okay, at this point I've presented a completed FPGA and DDR3 design that has actually been built and verified operational. I showed how we can set up the simulation of this design and presented the simulation results in various formats. However, I've been focused on just a single type of DDR3 operation, that of a data write. I did this in order to avoid confusion while I presented the overall simulation process. And while a data write does of course use all of the signals present in the design, the results were rather specific to that operation. In addition, when I laid out this board, I was able to follow all of the manufacturer's recommendations and best practice techniques, so there really wasn't much question as to the design working as planned. In fact, to be honest, it probably would not have even been necessary to perform simulations before going to fabrication, unless there were other aspects of the design that needed it. So now I would like to dig deeper into the design, examining some of the details relating to individual sections of the layout. I will also examine the effects and trade-offs that often occur when we are no longer able to follow best practice layout techniques. But before I do this, let's have another polling question. I would like to know, has the DDR that I've already done been at all interesting to you? So yes, it was informative, it's kind of helpful, interesting but not helpful, or not at all what I was looking for. Okay, I'll go ahead and close it out. It looks like about 50% said it was informative, so I guess I'll keep my job. Kind of helpful and interesting, the other half. Good. Okay, let's go ahead and get back to it. So to this end, I'd first like to look deeper into the care and feeding of differential pair signals. I will be using the DQS0 data strobe signal for my explorations, as shown here. There are, of course, a variety of aspects involved in routing a differential pair signal, but at this point I will focus on issues involving the relative lengths of the traces. I will discuss the importance of matched length traces later, but for this example, I've routed these signals to within 20 mils of each other, and as you can see, the overall routing is pretty clean. This clean routing is reflected in the simulation results as well. To show this, I'll first show the eye diagram of the data signals of the write operation, and then add in the data strobe differential pair signals, here overlaid in black. As we see, the strobe signals are very clean, and they transition nicely in the middle of the eye. Here's the same view as a regular waveform. As you see, it's a bit cluttered when the differential pair signals are included in the display. It would be much easier to understand if we just had a single clock edge instead of the positive and negative signals we see here. Fortunately, System SI can help us out by doing a little math and combining the two differential pair signals into a single waveform. Here, the blue signal represents the mathematical difference between the differential pair signals. So although we're ending up with a trace that has twice the signal height and is centered around 0 volts, we can now more clearly see the edges being used to clock in the data. We can also do the same thing in the eye diagram, although it ends up looking much like the previous version, except for the offset clock traces. To demonstrate what happens when the legs are not of the same length, I artificially introduced additional length to one of the legs of the differential pair and did the simulation over. In fact, I added a lot of length, almost 100 mils. This is 5 times the recommended difference between legs of a differential pair. And yet, when I did the simulation and examined the results, I found that the waveforms were almost exactly the same. Here, I've overlaid the negative DQS trace from the regular and the extended routing for comparison. The red trace is the extended length, and the green trace is the original routing. At the resolution we've been looking at, you can barely see there is a slight difference, but not enough that you would think it would be something we should be concerned about. Here, I've increased the zoom by a significant amount, and we can now see the actual difference. Using the marking tool in System SI, I measured the change to be about 15.7 picoseconds. Given that I know the physical difference is actually 100 mils, This calculates out to a propagation speed of 0.157 picoseconds per mil, which is comparable to the speed of 0.148 picoseconds per mil as determined by a field simulator based on the stack-up and trace dimensions. These numbers help me know that my simulations are working out as expected. Here is the eye diagram view in which I've added back in the data bus signals to provide our eye. We can see that there is some shift in the strobes where the red traces move to the right a bit. However, as I mentioned before, it doesn't seem to be all that much worse, and certainly doesn't seem like it would fail the design. So what's the big deal? Why are we told to keep the length so close, sometimes even to 5 mils or less? It's not affecting the timing much, so why worry about it? As it turns out, there is much more involved than just the logical timing of the signal. Mismatched differential pair traces and the resulting mismatched wavefront propagation have all sorts of adverse effects on noise immunity, EMI and EMC, and crosstalk. I won't go into much detail here, but if you want to know more about it, I highly recommend that you watch a webinar by my colleague Sean Kelly, in which he provides an excellent treatise on the inner workings of differential pairs and their signals. Suffice it to say that you should always match your differential pairs as closely as possible. Considering that most layout software provides tools to assist in length tuning, there really isn't much of an excuse not to do so. But what about the effects caused by the wiggles used to do the length tuning? Wouldn't they cause problems by introducing a lot of impedance mismatches along the line? For example, in my layout, I had to add a fair amount of length tuning for the DQS1 data strobe due to the pinout orientations on the two devices. You can see the wiggles I had to add in this section here. As it turns out, there really isn't much of a problem with the final signal integrity. The wiggles do affect the higher frequency components and introduce some reflections, but these are minor enough not to affect the overall integrity of the signal. If we compare the time domain waveforms of both DQS0 and DQS1, we really don't see much difference. Here, the red trace is the clean DQS0 signal, and the green trace is the DQS1 with the length tuning wiggles. Other than some offset due to the fact that the overall lengths are different, the shapes of the waveforms are pretty similar, certainly nothing to cause any concern. And if we look at them in the eye diagram, we also don't see anything that really should worry us. So the takeaway here is that mismatched trace lengths within differential pair routing have a far greater impact on the design than do the length tuning wiggles needed to match them up. I'd like to look at one more interesting thing about using differential pairs. As it turns out, they are remarkably resistant to having gaps in their return current path. Conventional wisdom states that you should never, ever, under any circumstances, have a gap in your return current path for high-speed signals. I've even said this myself in my previous webinars. But there turns out to be an exception to this rule, and that exception is the use of differential pairs. To demonstrate this, I've added a gap in the return current planes for all of the signals associated with byte lane 0. This includes both the single-ended data bus signals as well as the differential pairs for the data strobes. After performing the simulation and examining the results, we see that the single-ended data bus signals are a real mess. This is pretty much what we would expect when we put such a large barrier in the return current path. So that gap really messes up the signal integrity, huh? As you see, the waveforms are all over the place. This is especially evident when we look at the eye diagram. As you can see, there is literally no eye opening at all. So we can pretty much guarantee that doing something like this will cause the design not to work. However, when we examine the waveform for the differential data strobe signal, we see that it looks a bit wonky, but is not really as bad as the data bus signals themselves. And if we convert it to a differential signal, we see that it actually begins to start looking quite normal. Looking at it as an eye diagram really seals the deal. This looks like a very acceptable signal. Based on these observations, it seems that compared to single-ended signals, crossing a gap in the return path does not seem to affect a differential pair signal quite as much. I'll give my usual caveat here that I'm just showing a high-level analysis of this effect, so be aware that there are other aspects that you might need to deal with, such as the impedance mismatch of the gap section. But for the most part, you can balance things out and end up with a remarkably robust signal should your layout require crossing split planes. In fact, I think one of your biggest problems will probably be just convincing your colleague that it is okay to route things this way. I'd now like to touch on the topic of termination, if you'll pardon the alliteration. We saw some effects of termination when we were looking at the data bus signals. DDR3 provides for on-die termination in the memory devices themselves, which greatly simplifies the design and layout of the data bus signals. But what about the address, command, and control signals? Collectively, these are known as ACC. While on-die termination can be used for the data bus because they almost always use a point-to-point routing scheme, there are too many routing variations for the ACC lines to allow the effective use of on-die termination. For example, in the simplest routing case with only one memory chip, the ACC lines are also point-to-point. It may not need any termination at all. But the far more common situation involves at least two memory devices, and often a lot more. The ACC lines must be routed to all of these devices and in a manner that provides acceptable levels of signal integrity. In these cases, we have the option of using either a flyby or a T-branch routing topology. I'll explore these more later. In the DDR3 design I've been presenting in this webinar, I used what is known as flyby routing. Flyby routing is a new scheme that was first presented when DDR3 specification came out. Flyby greatly simplifies the routing and termination requirements of a multi-chip memory design, but at the expense of a more complex memory controller. However, I won't go into the controller details here since it really doesn't affect the PCB itself, other than to simplify the ACC routing and impose some length and timing constraints on their signals. With flyby routing, the ACC lines tend to get pretty long and therefore almost always require some termination to prevent unwanted ringing and noise. And in fact, the DDR3 specification suggests the use of what is called active termination for the ACC lines to get the best possible signal integrity. In the meantime, I've simulated the ACC lines for my design, which uses flyby routing and active termination, to provide our baseline data set that we will use for comparisons as I explore other termination schemes. Here I'm showing both the signal waveforms and the eye diagram. As you see, the signals are still a bit noisy and not quite as clean as for the data bus, but still plenty of eye opening is available. I would feel quite good about this design, and since I already know it works, my feelings are justified. As an aside, I'd like to mention that I could probably have tweaked the resistor values and improved the signal integrity if I really wanted to. This kind of termination tuning is pretty common in high-speed designs, but is usually only done once the board is fabricated. Since it's just a simple matter of changing resistor values, it's not a very expensive change to the design, and can even often help with EMI and other issues. Now let's explore some variations on this theme and try some other termination schemes. First off, we'll see what happens with no termination at all. To do this, I'm going to remove all of the components and traces associated with the ACC termination. I could probably just have turned off the VTT supply, but wanted to get an absolutely clean simulation without having the trace stubs hanging off. So to this end, here is the layout with the termination components still installed, and here it is with all of the ACC termination components and traces removed. As you see, I freed up a not insignificant amount of PCB space. Based on our results from removing the data bus on-die termination, we would probably expect to see some pretty bad signals. Surprisingly enough, this turns out not to be the case. Here are the waveforms for the non-terminated ACC signals. As we would expect, there's still some overshoot and ringing, and the levels are worse than with termination. However, they really don't look all that bad. And when we look at the eye diagram, we see that there is still plenty of opening in the eye. This tells me that this board design could probably have been built without using ACC termination and still have worked just fine, especially if it is not running at full speed, which is often the case for FPGA-based memory controllers. This is because the placement of the chips allows for relatively short routing lengths. The line lengths average about 2.5 inches, with the longest being about 3 inches. In addition, since there are only 2 memory chips in the chain, there is only one set of stubs on the ACC lines, thus minimizing the detrimental signal integrity effects. I'm now going to step away from this DDR3 design in order to better examine variations on the routing topology. I'll need to have more memory chips to play with and more flexibility in my routing options. So here is the new design I'll be using. As you see, it now has 4 memory chips in addition to the FPGA controller. I will be using the same devices and models as before, however. Also, since we're only doing this to compare different routing and termination schemes, I'm going to simplify things by only routing the address 0 line. As you see here, I've routed it using a flyby topology to provide baseline simulation data. In addition, I added some extra length between the controller and the memory chips, so the simulation data is a bit more realistic. And here is that simulation data, pretty much about as clean as you can get. The 4 waveforms represent the signals at each of the 4 memory devices. You can clearly see the time shift caused by the trace distance between the chips. And here is the eye diagram, but only for the signal to the last memory chip in the chain. It also looks pretty much like an ideal eye diagram. Okay, now let's take a look at what is known as T-branch or tree routing. T-branch was the default routing paradigm for earlier versions of DDR, since previous controllers could not handle the time shifts caused by flyby routing. However, just because DDR3 supports flyby routing does not mean that you always have to use it. There is no reason why you couldn't use tree routing in a DDR3 design should that work out better for you. As it turns out, there are several flavors of T-branch or tree routing. We have tree with VTT termination, tree with Series R termination, and a tree without Series R termination. The VTT option provides the best signal, but is typically considered overkill in a point-to-point system like the one I'm doing here. The Series R versions are typically the ones used for T-branch implementations. The Series R version itself provides a better signal integrity when the trace impedance does not match well with the devices. But in layouts that provide nice impedance matching, you could often do without the series resistor. And here's my layout done as T-branch routing without a series resistor being used. As you can see, I was able to make it very symmetrical with an almost schematic branching scheme. Pretty doubtful you'll see something as clean as this in the real world though. And here are the simulation results. I once again surprised myself when I looked at these results because I only saw 1 waveform even though there should have been 4. As it turns out, my layout was so exact that all 4 waveforms overlapped exactly. This was a great demonstration of the main reason for using T-branch topology. All of the branches are of about the same length, and thus all of the signals arrive at the DDR3 chips at about the same time. So if T-branching were used for the entire ACC group, including the clock, you can see how all of the signals would be clocked at the appropriate time. And here is the eye diagram. Unfortunately, we're seeing some eye closure as a result of the imperfect termination, which is causing some reflections. So here's a demonstration of the downside of T-branching. It's harder to get the termination right. While it might be possible that a design like this could be tuned to work without termination, let's put in a series resistor and see what happens. Here's the design with a 10 ohm resistor placed near the beginning of the branching. Why 10 ohms, you ask? Because our intent here is to minimize reflections, not necessarily match impedances. Using a resistance lower than the trace impedance tends to work best in these cases. In this waveform diagram, the simulation with the series resistor is shown in blue, and the red waveform is the no resistor case. As you see, we do have a slight improvement on the waveform, but the question is it enough? When we look at the eye diagram, we do see that it helps somewhat. Here, the red line represents the no resistor case, and the blue has the series resistor. It's a little hard to see, but the eye actually did improve somewhat. This tells us that if we were to tweak the resistor value just right, and maybe even tweak its placement, we could probably get the eye even cleaner. We could, of course, generate a JEDEC report to verify the operation. There is one more type of routing scheme I'd like to present, which I call the hybrid scheme. It is in effect a combination of both T-branch and flyby routing. I've modified my T-branch design to diagram how it works based on an actual design I did a while ago. That design had 8 memory chips with 4 on the top layer and 4 on the bottom. Here, the additional 4 chips are on the bottom layer, have blue pads, and are slightly offset so that you can see them in this view. And here is my routing scheme. I routed each group of 4 chips as flyby, but connected them to the controller as if it was a T-branch design. Given the tight component placement and routing constraints from the rest of the design, this was pretty much the only layout I could come up with that would fit. Fortunately, simulation showed that it would work just fine with acceptable signal integrity levels. I brought this hybrid concept up to reinforce the fact that you're not necessarily constrained to one specific routing paradigm for DDR3 layouts. As long as you end up with acceptable timing results and levels of signal integrity, you are free to do whatever you need to do in order to get your design and layout to work. For my final topic, I'd like to examine some of the issues arising from crosstalk. Crosstalk is a term used to describe the noise caused when electromagnetic fields of one signal trace intersect a nearby trace, causing unwanted voltages and currents to be created. While it is the fields themselves that cause the problems, it is more common and more intuitive to think of crosstalk as being caused by capacitive and inductive coupling. This lets us think of the source of the noise, known as the aggressor line, being connected to the victim line by a series of capacitors and inductors. In fact, this concept can actually be used to simulate physical designs, although here I'll be using a field solver instead. Okay, let's dive right in and look at some simulations, which I'll then use to demonstrate various causes and remedies for crosstalk noise. Since crosstalk noise is caused by overlapping fields, it makes sense that having long parallel traces close to each other would be something to avoid. And as we see in my existing design, I do have a fair number of parallel traces for all of the signal groups. You might think this would cause excessive noise, but since we've seen the resulting simulation data and know for a fact that the board works, it seems like these parallel segments are not failing the design. Let's explore this further. To keep things simple, I'll focus on just these two signals, which are the address 11 and address 12 lines. And as you see, they have a section that is routed in parallel and quite close. In fact, they are 5.8 mils apart, which already violates the 8 mil spacing recommended by Micron. And here are the simulation results. I've isolated the waveforms for these two traces to see what they look like. Other than the expected overshoot, they do look pretty good. However, in order to better examine the effects of crosstalk, I'll turn off the A12 signal in order to make it the victim trace. It is still terminated at both ends, of course, but it will just not have a signal present. After simulation, we have these results. We can clearly see some crosstalk noise being generated on the victim line, shown here in blue. However, it doesn't really seem all that bad. And when we look at the eye diagram, we see that there isn't much amplitude at all. Remember, this noise will be added to the existing signal, but even so, we're seeing it's not going to fail the device. This is expected since we know the board does work. So let's push things to the limit and see how bad I can make the crosstalk noise. I've routed the two signals to be as close as possible, about 4 mils. I've also increased their total parallel length to be about 900 mils. These numbers exceed pretty much any best practice guideline you'll ever see. And here are the results. Looks pretty much the same, huh? Definitely not a big enough difference to worry about, and certainly not as much as I was expecting. If we overlay the two address 12 traces from each simulation, we do see that the one with excessive parallelism, here shown in blue, actually is a bit worse, but not by very much. I think the main reason why this is so is that we have relatively slow signal slew rates on our transitions, combined with the fact that these signals are well terminated and of relatively short lengths. The crosstalk noise just doesn't build up enough to cause problems. To wrap up the topic, let's do a quick simulation of the design that separates the two traces as much as possible, even greater than the suggested 2 times trace width distance. And here are the results. The red trace is from our first design, and the blue trace is with the widest possible separation. Some slight improvement, but once again, not really that much difference. And here I've overlaid the worst case routing, shown in green. To be honest, I think at this point we're really seeing more ground bounce than crosstalk. So it seems like this design is relatively immune to crosstalk issues, at least on the ACC lines. Of course, to be sure, we would check any other traces as well, but I think we can conclude that if the design has good termination and does not have fast slew rates, you probably don't have to worry all that much about crosstalk, even for relatively long parallel traces. Although this example of crosstalk was interesting, I found the results less than satisfying. Therefore, I'd like to delve a little more into the concept of crosstalk. To do so, I've created a new simple design case with just two parallel traces. One trace will be the aggressor trace with a driver on one side and a termination resistor on the other. The other trace will be the victim trace and will be simply terminated on both ends so that any crosstalk noise will not bounce around. For the driver, I'll be using the same IBIS pin model as I used for the address pins on my FPGA, although I'll only be driving it to 1 volt to make the simulation a little bit easier. And here is the layout. Since I'm able to assign component models from within the simulation software, I don't need to have any footprints here. Instead, I'm just using vias to mark the various endpoints and ground connections. I've made 4 variations of this design, changing only the spacing between the traces. This will let me explore what effect the spacing has with no other variables in the equation. Since spacing recommendations are usually given in terms of multiples of the trace width, I created 3 designs with 1x, 2x, and 3x spacings. The 4th design will have the closest possible spacing of about 4 mils. I'll then examine each of these designs in both the frequency domain and the time domain. Here is the S-parameter graph of the first design, the worst case 4 mil spacing. In this graph, the higher the amplitude of the signal, the more energy is being transferred as crosstalk noise. So we'd prefer to see the lines with lower amplitudes representing less crosstalk. The red trace represents what is known as near-end crosstalk noise, and the blue trace represents the far-end crosstalk noise, with the terms near and far relating to the driver end of the traces. The importance of near and far-end noise is more apparent in the time domain waveforms. And here is that waveform. The green trace represents the driver signal, essentially just a square wave using the FPGA address output pin model. And as before, the blue trace is the far end and the red trace is the near end crosstalk noise. As we see here, the near end crosstalk noise starts at the same time as the driver transition edge, which makes sense since they are right next to each other in the layout. The far end noise at the other end of the trace doesn't kick in until the signal has had time to traverse the entire trace. Thus, the bump in the blue trace is also indicative of the propagation delay of the signal. In this worst case scenario, I'm generating noise pulses of about 0.1 volts, both positive and negative. Since the driver signal is 0.9 volts, we're looking at a noise margin of almost 10% of the total signal. This is not good. Now let's look at the second case with 1x trace width spacing. Here I've put its S-parameter graph next to the 4 mil spacing graph for comparison. As you can see, the amplitudes of the lines are lower, which indicates that less energy is being transferred as crosstalk noise. This is what we would expect since there is less electric field overlap between the traces. And here are the time domain traces. As you can see, the amplitudes of the red and blue traces are lower in the 15 mil spacing scenario, also indicating less crosstalk noise is being generated. As you would probably expect, this trend continues for the remaining 2 design cases. I've shown all 4 S-parameter graphs here for comparison. You might find the 3x spacing case particularly interesting, since there is essentially no trace at all. This means that there is no calculable crosstalk between traces spaced 3x apart, which is why this dimension is usually given as the desired best practices spacing. And here are the time domain waveforms. I've chopped off the driver signal since we're just interested in the noise signal traces. As you see, they also follow the same trend, ending with no measurable noise for the 3x spacing scenario. I think these design cases were a good demonstration of both the effects of crosstalk noise and the means of mitigating these effects by increasing the intra-trace spacing. This concludes part 3 of my 1-part series on practical aspects of signal integrity. Here is an overview of the topics I covered over the course of these 3 webinars. My intent for this webinar series was to give you an overview of how various signal integrity concepts can apply to your designs, and how simulation can give you more information when making your design and layout decisions. It's been quite a journey of exploration, and I hope you found it as interesting as informative as I have. And I'd like to end as I started by quoting the inestimable Mr. Eric Bogatin, who states that there are 2 kinds of engineers, those who have signal integrity problems and those who will. So hopefully at this point you have a better understanding now of what he is actually trying to say. As signal speeds get faster and layouts get tighter, issues involving signal integrity are moving to the forefront of concerns for the PCB designer. It is getting to the point that it's just no longer possible to design and route a PCB nowadays without being conversant about the core concepts of signal integrity. And as we've seen, simulation now plays an important role in the design and verification process for high-speed systems. So unless you have the time and money to spin several versions of your hardware, simulation will have to become a critical part of your design process going forward. Okay, let's wrap things up with one final polling question. What did you think of my topics? And they were a good, just the right amount of topics, a little bit too much maybe, not enough, give me more, way too much, give me a break, or they were way over your head. It looks like 75%-ish said it was good. That's good to hear. 20% one more, which is also good to hear. So I appreciate all of that. And with that, I'm going to go ahead and turn it back over to Paul.
All right, thank you very much here. I'm going to just switch the screen over. And by the way, please do feel free to ask any questions there. Tom, you already have a couple of them queued up for you. And what I'd like to do is just spend a few moments talking about 9.connects here. So you're here for a reason, and probably one of three reasons. As Eric Bogerton alluded to, you probably have signal integrity issues, or you're anticipating signal integrity issues, or you want to see some real world examples, which Tom did a really great job in showing here today. What does simulation require? Well, Tom kind of gave you a hint over there as to what we've seen is necessary. Number one, there's a cost of the tools. Secondly, there's a time to learn these tools. They're not necessarily simple out-of-the-box solutions. And then there's also a time that's necessary to set up a workflow. What you probably didn't see is the amount of time and energy that is necessary to take something from any ECAD tool and to bring it into the Cadence Design System Security tool here. And then there's also time to set up the initial conditions, which is what Tom talked about here initially. And lastly, as you can see, it's important to know how to interpret the data. In fact, he had to continue to look at data, as you saw towards the end, in order to determine if what he was seeing was real. So in short, there's a lot of time and money involved in this if you're going to go this route of simulation. So what can we do for you here at 9.connects? Well, when it comes to the cost of the tools, we've already got them. So if you're looking for some assistance, we've already got them. We can make use of them. And more importantly, the time to learn the tools, well, that's what Tom has done here. We've done that here. We've learned the tools. The time to set up the workflow, well, guess what? He spent a lot of time doing, as I just mentioned that. So the workflow is already set up to go as well. And also the time to set up the initial conditions. So every board is going to be different, and we know how to do that. And lastly, of course, knowledge and to interpret the data. So the short of it is, let us put our simulation knowledge to work for you. So if you're interested in simulation, before you go out there and put down the money and try to put the time into it, come talk to us and see what we can do for you. And of course, for more information, check us out at 9.connects. All right, well, thank you very much, Tom, for your presentation today. I really appreciate that. And thank you out there for joining us here today. And we will be holding our next webinar, just to let you know, for November. It will be on the 20th rather than the 27th due to the Thanksgiving week. So with that, again, thank you very much for joining us here today, and you have a wonderful day.